So now in this class we are going to discuss about the chemical properties of ozone. We know that the ozone is a very strong oxidizing agent, and it is an oxidized oxygen. We used to say that. So that is we used to say that it is having it will react with almost all the reducing agents, and in mainly it shows the maximum oxidation. Suppose we are having H2S, it will convert into H2SO4. It shows maximum oxidation. Why it is so? Because of its strong oxidizing character. So we used to say that in case of ozone, we write that it is like this. So we are going to discuss that is the chemical properties of ozone. So properties of ozone we are going to discuss. That is, we can say that. Now we can write the reaction of ozone with, we'll say that, write the reactions of ozone. So we'll write that it is the oxidizing character. First we can discuss about the oxidizing character. So oxidizing character of ozone, if I discuss that is, we are having the ozone, then in presence of, if I write that, it is in presence of acid. Suppose I write like this, that is in presence of acid. So O3 when treated with acid, that is H plus sign plus electrons, then will get converted into the O2 plus, we'll write that it is, we'll write that twice of this, twice of electrons, so that I'm going to write that H2O. So in this case the E0 value is around, that is I'm going to write that SRP value. So standard action potential value of ozone in acidic medium is E0 value is around 2.07 volts. And if I write that ozone, that is like we are going to write that it is 2 electrons, and we'll write that it is H2O, so that we'll write that it is O2 plus, that is OH negative ion. So I'm going to write that it is O2 plus OH negative ion. The E0 value, the SRP value in this case is, if we talk about that, E0 values, that is also called the SRP value of ozone. In this case, I'll write that it is 1.24. So if I write that it is 1.24, so and I'm writing that it is plus, we know that both the cases I'm writing that it is plus 1.24 volts and that is 2.07 volts. So in acidic medium it acts as a strong oxidizing agent rather than in basic medium. So it is a powerful oxidizing agent. Powerful oxidizing agent in acidic medium. Oxidizing agent in acidic medium, we used to say that acidic medium, then in basic medium, then in basic medium we used to say that. So then in basic medium we used to write like this. So that is how we can explain on the basis of SRP value, because SRP value means tendency to gain electrons. Tendency to gain electron means it is its oxidizing character, because oxidizing agents are those which have tendency to gain electrons. So we can write like that, that is a powerful oxidizing agent in presence of, right? We'll say that acidic medium. Now we can write that, we can write this as A part, now we can write that B part. B part in basic medium, we used to say that, basic medium, the reaction in basic medium, I'm going to write that, it is like this. So Ki reacts with, we'll say that the Ki reacts with O3 in the basic medium to get converted to KiO3 and O2. That is the basic medium. But in acidic medium, we have seen that it converts, that iodine is liberated. We have seen in the estimation. So that is in basic medium, it gets converted into this. Whereas if I write Ki with the O3, it can also convert it into that, depending on this. If it is thrice of this, we'll get that KiO3 plus, we can write that O2. So that is 9. So I'll write that 6 here. But if it is like this, suppose, and if I write that Ki plus 4 O2 O3, then in that case that is an excess. Then this, then it converted into KiO3 plus KiO4 plus, we can write that O2 is liberated in the reaction. So we write that it is like this. The reaction is like this. So this is periodate, potassium periodate is formed, iodate is formed. This is potassium iodate is formed in this reaction. So this is potassium iodate is formed in this case. Potassium iodate and potassium periodate is formed in the reaction like that. So we can say the reactions are like that. Now even the KMnO4 reacts. So if I write that the reaction with KMnO4, the ozone reacts with that is K2MnO4, that is K2MnO4 when reacts with ozone, so it can be used for the preparation of KMnO4. So it will get converted into the KMnO4, that is plus 6 oxidation state to plus 7. So it is the loss of electron, the oxidation of this. So oxidation of this in aqueous solution, we are going to write that obviously we are going to add water in this, so that we are able to write that the KOH is formed as well as the oxygen is formed in the reaction. So I am going to write that the 4 KOH is formed here, twice of KMnO4 will get that, and we get the oxygen in this reaction is. Then H2S also react with, then ozone also react with H2S. If I write that with H2S, that is a reducing agent, it will get converted into the sulfur, that is a yellow compound, yellow PPT, plus we get that's the twice of H2O. So I'll get that sulfur plus thrice of H2O. So I'll write this as like this. So it will give us the yellow PPT with the H2S, what we can write is. Now I2 which is reacting, now we'll say that I2 which is reacting in a dry state. So it is a dry iodine when it reacts with the ozone. So when dry iodine reacts with the ozone, it will get converted into I4O9. So that will convert into I4O9 plus 9O2. Plus 9O2, we'll write that, and we are able to balance that. So in this case, that is excess of ozone is used in the reaction. That is all. Where we can write that here, where I4O9 is, that is I positive and IO3 negative whole thrice. It exists as a solid. And this indicates that if I has a positive charge, its basic character. So we say that it explains, it indicates its basic character. Basic character, we know that. So it is going to indicate its basic character, because in basic character they are having a salt-like structure. So if any atom has a positive charge, it will act as a base. Obviously, Na positive, it is basic, like that. So it will show its basic character. Even silver reacts with ozone. So we can write that even silver reacts with ozone to get converted into Ag2O, that is a black PPT is formed, and we get that O2. So even it reacts like this. Then we can write that even H2O2 reacts with ozone. So it is an oxidizing agent. Then H2O2 will convert into H2O plus O2, we can write that. So it will convert into H2O plus O2, and we get like this. That is the reaction what we have. Similarly, if I write that it is the reaction, other reaction, that is if I treat KOH with the O3, if I treat KOH with O3, then I got orange color solid, that is called the potassium. We used to write that it is an orange solid, sesquioxide. So orange solid, that is called potassium sesquioxide. So potassium sesquioxide. Oxide is formed in the reaction. That is how. So we used to write that it is an orange solid which is formed in the reaction when KOH reacts with ozone. It forms potassium sesquioxide plus O2 plus H2O. Obviously, we can write like this. Here we can balance that as that is twice of KOH, 5 of this. Then we can write that it is H2O, then KO3. So I got this as O2, then 3, then I'll get that 6 O2. So like that we are able to balance the reaction. So that is how we are able to write that it is, I've tried this as twice, then I'll have to write this 5. So we got that the balanced reactions. Now if I write that uses of ozone. So if I have to write that uses of ozone. This is a chemical reaction now. Now if I have to discuss the uses of ozone, then it is used as, it is used in preparation of KMnO4. You can see that reaction we have already written there, the preparation of KMnO4 from reaction of ozone. So it is used in preparation of KMnO4 ozone, that is it is used in oxidative bleaching. It is used in oxidative bleaching, right? That is a permanent bleaching. So bleaching, that is permanent bleaching. We used to say that permanent bleaching. So if I write that permanent bleaching, that is we can say that it is like this. So O3 get decomposed to form O2 plus O, nascent oxygen. This nascent oxygen which is formed will react with the colored matter. Colored matter, and it converts into the colorless matter. Colorless matter when it reacts with the nascent oxygen. So we get like this. The colorless matter is formed with that oxidative bleaching is. So it act as germicides. Germicides. That is, we used to say that disinfectants, and so used for sterilizing the water. Sterilizing water. So it is used for the sterilization of water. And there is one more property, that is tailing of mercury. So the tailing of mercury is the tailing of mercury. So actually what happens, mercury flows, it has high meniscus when it is present in a glass jar. So mercury when reacts with ozone, it forms that mercurous oxide by losing its meniscus. So tailing of mercury. When ozone reacts with mercury, when Hg reacts with O3, it will convert into Hg2O plus O2. That is going to form, that is Hg2O plus O2. So it starts, that is pure mercury, but it should be the pure mercury that is going to react like this. So it, right, that is starts staking the glass. Staking the glass and forms a tail when flows on the glass. Because mercury that flows on the glass and drops, it doesn't form a tail, but when it reacts with ozone, then it will form a tail like this. Otherwise it will flow in drops like this. So it forms a tail because it starts taking that glass when it reacts with the ozone. This is called tailing of mercury. So this is about the ozone, what we required is, and the part which we have to study about the ozone is. So that's all about the ozone, what we have to discuss is. So these are the reactions, the chemical reactions and the information about the ozone which is required by us. So that is all about the ozone is. Next we can start is the sulfur part. So this is about the ozone. Now we are going to start the sulfur. These are the chemical properties of ozone, what we have written, and these are the SRP values from which we are able to tell that the ozone is a strong oxidizing agent in presence of acid. It also acts as an oxidizing agent in presence of base, but it is weaker oxidizing agent in presence of base than in presence of acids. So that is about that. We can say that the ozone, what we required is. Next we can discuss about the sulfur. So let us start that sulfur. So we are going to start sulfur now. So if we write that sulfur, it exists as S8 we are talking about. So it will have an elemental form, that is what we say that it is in form of S8. So let us check that what is the information we required for sulfur. Sulfur exists as S8. So there are many allotropic forms of sulfur. It is monoclinic sulfur, triclinic sulfur, orthorhombic sulfur, plastic sulfur, right? Milk of sulfur, like that. A rhombic sulfur or a monoclinic sulfur, they are crystalline form. The plastic sulfur is the amorphous form of sulfur. But rhombic sulfur or the monoclinic sulfur, they are the crystalline sulfur. We used to say that. So we can discuss about the sulfur, its structure, and what are the properties what we required is. how we are going to prepare the sulfur is. So let us check what is sulfur, what we require in the sulfur. It forms many allotropes, of which we can write that it forms many allotropes, of which we used to say that the rhombic sulfur. The rhombic sulfur, it is also called yellow sulfur. Rhombic sulfur, that is also called the yellow sulfur. It is yellow in color because, so we call it as a yellow sulfur. And that is a rhombic sulfur. The yellow sulfur, it is also called alpha sulfur. And the monoclinic sulfur, so yellow sulfur or alpha sulfur. And the monoclinic sulfur, that is clinic sulfur, that is called beta sulfur. Sulfur, that is called beta sulfur, generally exist. These are the two sulfur generally they exist in nature. So is present in that is nature. So they are the two sulfur which are important to us. So it forms many allotropes of which this and this is important for us. We will say that these are two important sulfur for us. So these are the two sulfur which are important. One is called the rhombic sulfur, other is called the monoclinic sulfur. Then we can say that how that the rhombic sulfur, which is stable at room temperature, on increasing the temperature will convert into the monoclinic sulfur. So we used to say that the rhombic sulfur stable at room temperature. So stable at room temperature, we'll say that room temperature when it is heated, that is when it is heated at we can say that equal to 369 Kelvin, then that case it will get converted into monoclinic sulfur. So this is the monoclinic sulfur, that is the beta sulfur, we used to say that. So the alpha sulfur on heating at 369 Kelvin. So we can say that the 369 Kelvin is a transition temperature. Therefore, we can say that. So 369 Kelvin is a transition temperature. Transition temperature, we can say that. Because below that it is alpha sulfur, above that it is or equal to that it is monoclinic sulfur. So that is beta sulfur. Temperature. So that is called the transition temperature. So this is about that is the rhombic sulfur and the monoclinic sulfur is. Now what we can do is, that is, let us discuss about that the rhombic sulfur. Separately we'll discuss that what is rhombic sulfur and what is the monoclinic sulfur is. So if I talk about that rhombic sulfur, we can say that the difference in rhombic sulfur. So write that rhombic sulfur, that is we say that it is alpha sulfur, that is a rhombic sulfur. We used to say that is the yellow color alpha sulfur. So we used to say that in that case the rhombic sulfur, we are going to write that it is alpha sulfur, the yellow color. Melting point is 385.8 Kelvin. So it is yellow color sulfur, yellow solid. We used to say that. And melting point, we used to write that it is equal to that is 385.8 Kelvin. Its melting point is this. So it is a yellow color solid with a melting point of this and the specific gravity of. And its specific gravity is that is 2.06 that is gram per centimeter cube. So we used to write that this is the 2.06 gram per centimeter cube. We used to write that is the specific gravity of this. So it is the rhombic sulfur when it is dissolved in carbon disulfide. So when dissolved in carbon disulfide, when the sulfur, that is S8, dissolved in that is when sulfur is dissolved in carbon disulfide, then on evaporation we get the crystal of sulfur, that is called the rhombic sulfur. So when the crude sulfur, we can say that the crude sulfur is dissolved in, it doesn't dissolve in water because it is non-polar, so it doesn't dissolve in water. So when the crude sulfur is dissolved in carbon disulfide, then on evaporation of carbon disulfide we get the crystals of sulfur, that is called the rhombic sulfur. So when the crude sulfur is dissolved in carbon disulfide, then on evaporation we get the crystal of sulfur. Then on evaporation we get that crystal of sulfur. Get the crystal of sulfur that is called that rhombic sulfur. Crystals of, you can directly write that crystals of rhombic sulfur. So that is rhombic sulfur is, that is how we get the rhombic sulfur. So that is how we used to obtain that from the crude sulfur, how we get that rhombic sulfur is. So they are evaporated in this form. It is insoluble in water but readily soluble in carbon dies, that is sulfide. So but it is insoluble in water. So it is insoluble in water but readily soluble in carbon disulfide. So it is insoluble in water and it is but dissolves, that is readily soluble in carbon disulfide. So readily soluble in CS2. But it dissolves to some extent in alcohols like that, right? Alcohols and ethers. So soluble in CS2. And we used to say that is it dissolves to some extent in alcohol and ethers. And it dissolves to some extent. That is dissolves to some extent in that is alcohol and ethers. Alcohol and ethers, we can say that. So this is the information what we required about the rhombic sulfur is. Now we can check about the monoclinic sulfur. So if we talk about that monoclinic sulfur, we can write like this, that is the monoclinic sulfur. So monoclinic sulfur, we can say that we can say that monoclinic sulfur. So it is a beta sulfur of melting point. We can write that it is also called the beta sulfur, that is having a melting point of. It is a solid of melting point that is equal to 393 Kelvin. Its melting point is higher than that of rhombic sulfur. So monoclinic sulfur, it is having a melting point of this, and the specific gravity, but its density, the specific gravity is 1.98. So specific gravity is equal to 1.98 grams per centimeter cube. So its specific gravity is less. Now in this case, when a crude sulfur for its preparation, it is obviously soluble in we say that it is soluble in carbon disulfide. So it is soluble in carbon disulfide. So it is soluble in, that is CS2. That is its property, we can say that. So it is soluble in carbon disulfide. It is prepared by rhombic, that is rhombic sulfur melting and cooling till we say that. So what we say that that is when the rhombic sulfur. So rhombic sulfur, what we have, rhombic sulfur is melted and that is poured in the holes in earth crust. Then after few days, that is earth crust, in the holes of earth crust. Now what we will do is holes in the earth crust and remaining liquid that is poured in it, or so on removing the crust, the colorless needle-shaped crystals of beta sulfur are formed. So in the earth crust, and for few days, then after removing the crust, we get the crystals of white crystals of sulfur. So crust, we get the white crystal of sulfur. White crystals of sulfur. These white crystals of sulfur is nothing but the monoclinic sulfur is. Sulfur, that is colorless needle shaped crystals are formed. So that is colorless, that is white colorless needle shaped, that is crystals of sulfur are formed. So the temperature below 369, it will exist as a rhombic sulfur, whereas the temperature above 369 or at 369, it is the monoclinic sulfur, we can say that. So we can say that it is formed up by heating, that after a few days, then the removing the crust, we get that the needle shaped white crystals of sulfur are formed. So that is how we get that the monoclinic sulfur is. So that is how we are going to prepare the monoclinic sulfur. So this is the preparation of monoclinic sulfur is, we used to say that both alpha and beta sulfur, we used to write that both alpha and beta sulfur, that is the rhombic and the monoclinic sulfur exist as S8 in a puckered ring shape. Puckered ring in a, we can say that, and has a crown shape, we can say that, and has a crown shape. So that crown shape will be like this. We can write that the sulfur, we are going to write as like this. We'll make a crown like this. That is how we can make a crown. So we'll write that it is like this. So that is 4 plus 4, that is like a crown. You can see that that is like a crown. So this is a crown shape of S8 is. So both exist in that crown shape, the S8, the structure of S8 is. Other molecules are isolated with other molecules molecules with 6 to 20 sulfur is isolated. Sulfur is isolated, that is by heating that. Molecules that is 6 to, that is sulfur atoms per ring are isolated by methods, or by heating sulfur, by heating S8. So others are also formed as by heating. The S6 exists in a chair form. So we used to say that the S6 exists in a cyclohexane ring of chair form. So cyclohexane ring in chair forms. We already know that the carbon chain in cyclohexane ring, that is chair and board form. Then rings and this at high temperature, we used to say that at very high temperature, we used to say that is around 1000 Kelvin. The dominating sulfur is, we used to say that sulfur which exists is, that is S2 is formed. So that is the sulfur is, that is in form of S2, which is paramagnetic as we have O2, which is paramagnetic as O2 is. So which is paramagnetic in nature as O2 is. So O2 is also paramagnetic even though it has an even number of electrons, and similarly S2 will also be paramagnetic in nature according to the molecular orbital theory. The chair form of sulfur is like this, that is sulfur in a chair form, it will be like this. No doubt we are going to write like this, the chair form of sulfur. So we'll write that the chair form of sulfur will be like this. So this is the chair form of sulfur. Chair form of S6, we say that. And this is S8, that is a crown shape of S8 is like that. So that is how we can write that about the monoclinic sulfur, and the rhombic sulfur is the information about the rhombic sulfur, how that rhombic sulfur is converted into the, that is we say that monoclinic sulfur when it is heated at the 369 Kelvin, that is a transition temperature, and how it is converted. We know that the sulfur which is rhombic sulfur, it is poured in the holes which is made in the earth crust. We'll pour that in that for a few days, and after removing the crust we get the needle, crystalline needle shape white crystals are formed, that is called the monoclinic sulfur. So that is about that monoclinic sulfur is. So this is about the sulfur. What we required is, the other one is, we say that the plastic sulfur. So I can write that the plastic sulfur. So plastic sulfur is, these two are the crystalline sulfur. This is, we can say that this is amorphous sulfur. That is amorphous in nature. We will write that amorphous sulfur, the plastic sulfur. So actually what happens when sulfur is heated, so formed when the molten sulfur is poured in cold water, formed when the molten sulfur is poured in cold water. So in cold water, since the freezing, the setting, since you can say that the fusion takes place very fast. So if the fusion takes place very fast, then it will not have a crystalline sulfur and it will have, we'll say that random close packing in the cold water. Due to that random close packing, we used to say that it is amorphous in nature. So it is a chain-like molecule and rubber-like properties. A chain-like molecule and rubber-like properties. But on stranding it will get properties, but on stranding it will slowly convert it into the rhombic sulfur. So that we used to say that, and on stranding it becomes brittle and convert to rhombic sulfur. On stranding it becomes brittle and convert to rhombic sulfur. Stranding it becomes brittle and converts to the, we'll say that, and it will converts to the rhombic sulfur. And it will convert into the rhombic sulfur. So that is how that plastic sulfur is. This is the plastic sulfur, but we can say that it is amorphous, whereas the rhombic sulfur and the, we say that monoclinic sulfur both are, that is, both are crystalline form of sulfur. So this is about that information. What we required about the sulfur is as it exists as an acid, exists as the crown shape. This is a crown, what we can say is, that is a crown shape of sulfur, and the other rings also formed depending on the temperature and depending on the conditions what are used for heating the sulfur. So this is about that, we can say that the requirement for us for the sulfur is. Now from this you can say that the melting point of monoclinic is 393, whereas the melting point of this is 385. But we say that the rhombic sulfur is the elemental sulfur. So we used to say that we can write that note, the thermodynamically most stable sulfur. Thermodynamically most stable sulfur is, we used to say that is rhombic sulfur. So delta H of formation of rhombic sulfur is equal to 0. So that is how we can write that the information about the sulfur what we required is. So that's all about the sulfur. We can say that what is the requirement of sulfur is, we used to say that. Now we can discuss about that this is the information we required for the sulfur is. Next we can discuss is, that is about, we can write that the compounds of sulfur, we can say. We can write the compounds of sulfur. So if we discuss about the compound of sulfur, we can write like this, that is the compounds of sulfur. Compounds of sulfur, we can say that. So the compound of sulfur, we can say that is, the very first we can write is, that is sulfur dioxide. So if we discuss about the sulfur dioxide, we can write that that is So2. That is one of the compound of sulfur is, that is how. So if we write that the preparation is, so we first write the preparation methods of the sulfur dioxide. We can write that the preparation methods. So when sulfur reacts with air, that is O2, I will say that it is going to react with oxygen or air, it will get converted to O2 and that is SO3. But SO3 which is formed is around 6 to 8%. But mostly it is SO2 which is formed in the reaction. When sulfur reacts with, we used to say that oxygen directly, then that is the product of the reaction what we get as in the compounds of sulfur. Next we can write is, we can say that for the preparation of sulfur dioxide, the lab preparation method is, so we can write that the next one, that is the lab method for the preparation of sulfur is, sulfur dioxide is, we used to say that when H2SO3 is, when H2SO3 aqueous, right, is heated, I got that SO2 plus H2O. That is what we get as. So we get that when aqueous H2SO3 is heated, then in that case we get that the gaseous state this in gaseous state and this in liquid state. So that is what we get on slow decomposition. That is how we can get the lab method. The industrial method, that is the commercial method. So industrial method, we say that for the preparation of SO2, we can write that it is the industrial method is when FeS2, that is FeS2, when reacts with oxygen, it gets converted into Fe2O3 plus SO2. That is the industrial method for the preparation is. So it is 11O2, we'll write that twice of this and I'll get that 4 of this. So that is how we can balance this, the reaction is. So we get that it is 11, we'll write that this is 4. Now this will be twice and this will be sulfur, that is, we'll get that it is 8. So this is the balance reaction we can write. So here I'll get that is how we are able to balance that, and we'll get that industrially it is prepared from the iron pyrites. So this is iron pyrites which will get converted, it will react with O2. This is iron pyrites. So iron pyrite, that is having plus 1, that is minus 1 oxidation state in this, because iron will be plus 2 in that. So there is an oxidation reaction by oxidizing the iron pyrites, we get that Fe2O3 and SO2. So this is the method for the preparation of SO2 is. Now these are the method for the preparation of SO2. Now we can write the properties of SO2. So we can write that the properties are, if I write the properties of SO2, we can write like this. The properties is, it is a colorless gas and a pungent smell. So we can write that it is a colorless gas, which is colorless gas with a pungent smell, soluble in water, which is soluble in water. Soluble in water, we used to say that. So it is soluble in water because it reacts with SO2 to form H2SO3. So it is soluble in water. So that is how we can write its properties. It is a colorless gas. You know that it is a colorless gas. It liquefies at room temperature. It liquefies at a room temperature. So it can be easily liquefied at room temperature at 2 atmosphere. But the pressure should be higher than the atmospheric pressure. And the temperature should be, that is at 298 Kelvin, which is, and it boils at, that is its boiling point. So boils at 263 Kelvin. So it boils at 263 Kelvin because at room temperature it exists as a gas. So that is its property. The next property we can write is we can write that this is one property. The another property we can write it as that is with water. The reaction with water with NaOH we can write like this. It is an acidic gas. Acidic gas. So I can write this as, that is when it reacts with water, that is SO2, it forms H2SO3. So if it is an acidic gas, then it will react with the base. If you treat that with the base, any base, you'll get that the product of the reaction like this. So if I treat that, so it react with base. So it react with the base as, so we can write that when Na2OH, when it reacts with SO2, I'm going to write that it has Na2SO3 plus H2O is formed in the reaction. So that is how I'm going to write that the reaction is. So it will react with base as I have written that. It will react with base like that. Now SO2, which is also reacting with. So if I have SO2 in excess, it will react with NaOH. And if that is used in excess, then it will react with this Na2SO3. So it will say that Na2SO3 that is present in the aqueous solution. So water is already present there. So with H2O, it is going to form NaHSO3. So I'll get the product of the reaction is like this. So if you add a small amount of SO2 in NaOH, we'll get that sodium sulfite. This is sodium sulfite. So we get that sodium sulfite as the product of the reaction. But if sodium sulfite, SO2 is present in excess, then it is going to form sodium bisulfite. So sodium bisulfite is formed in the reaction. So that is the sodium bisulfite which is formed in the reaction is. Next we can write is that is SO2 react with oxygen with in presence of vanadium pentoxide, that is half O2, it convert into SO3. That is the catalytic reaction, we can say that, of SO2 is. So we can write like this. Also we will write that is A part. B part we can write that SO2 reacts with Cl2, you can say that. When it is reacting with Cl2 in presence of charcoal, so it will get converted into that SO2Cl2, that is called sulfuryl chloride. So this is sulfuryl chloride is formed in this reaction. So it is used for the preparation of sulfuryl chloride, we can say that. Another we can say that these all are the oxidizing properties of SO2. We can write that. Another is, we can say that its reducing property, we can say that. So reducing property is like this. So its reducing property, we can say that it is like this. The reducing property we can say. So in reducing property we say that if Fe plus 3, when Fe plus 3 reacts with SO2, then in that case it will get converted into Fe plus 2. So with water it is going to convert into Fe plus 2 plus I can write that that is twice of H plus ion plus sulfate ion, we get like this. So we get that it is we won't require this, we can write that Fe plus 2, the sulfate ion is formed from this and this. And to balance that, we can write that the H plus ion is. So you can write like this. The twice of this, I can write that it is how we can write the reaction of this is. Then similarly, I can write that if I am going to write that MnO4 negative and treated with SO2 in presence of, you can say that in that is water. That is again twice of H2O, it will get converted into, because it is acidic in nature. So Mn plus 2 plus SO4 2 negative plus you can write that H plus I. So you can get the reaction like this. You can get the reaction like this, Mn plus 2 sulfate ion, and we are going to write like this. This is 5, this is twice. So I got this is 5 and this is twice. So that is how we get the reaction is. So this was its reducing property is. Next we can write that it is angular shape and exists in two canonical forms. So its structure we are going to write that. If I talk about the structure, we can write like this, that is, we can write that structure of this, it exists in two canonical form. So exist in two canonical form with sp2 hybridization and planar structure. That is, you can write that angular shape. So the angular shape, it is like this, sulfur which is having a lone pair on this, that is like this. We are going to write that the double bond O and the double bond O, we can write like this. So the sulfur dioxide exists like this. So these are sulfur dioxide, we can write as. So that is how we can write that is. So, and the two canonical structure, if you want to write as, you can write like this, that is, or you can write like this. You can write like this. So that is how we can write that the two canonical structure is. So it will write like this. The other reactions we can write is other reactions of SO2. So other reaction of SO2 we can write is, we can say that about the other reaction of SO2 is, that is, It reacts with the PbO2 plus SO2 gets converted into PbO, that is the reducing character. So it will convert into that as PbSO4. Then I'll write that it is, we can write that other reaction as PbSO4. Then with magnesium when it reacts with sulfur dioxide, it gets converted into MgS plus MgO. The reaction is like this. So I'm going to write that it is twice, it will be like this. The reaction is. So the magnesium reacts like this, it is twice of this. So I require thrice of magnesium like this. The magnesium will react like this. And if I write that if it is SO2 is reacting with potassium with SO2 will convert into K2SO3. Directly react with metals. It is so much reactive. And with KiO3 it liberates iodine. So KiO3 when reacts with SO2 in acidic medium, we'll say that H2SO4 it gets converted into, it will liberate I2. So it will liberate I2 plus H2SO, that is K2SO4, we can write that. The K2SO4 and that is, you can write that it will be in presence of water, we can say that. So in presence of water, we'll write that is K2SO4 plus, you can write that H2SO4. That is how the product of the reaction can be. So this is SO2, not SO3. So that is, so we can write that with KiO3, it reacts with SO2 and that is water. SO2 and water, we can write that. So it reacts with SO2 and water. It is, we can balance it by redox reactions, that is, so I'll get that 5 SO3, that is 1 sulfate is there. So we can write that H2SO4, so we'll get that 4 sulfate will be there and 1 K2SO4, so we'll get like this. So that is how the other reactions are. It shows oxidizing properties like this. So it shows oxidizing properties, we can say that shows the oxidizing properties like this, that is oxidizing properties with H2S, we can say that SnCl2 with other reagents like we'll say that Hg2Cl2, CO and Fe. So with Hg2Cl2, CO and Fe, etc. we can say that. It shows the oxidizing properties with these. So we can write like this, that is the reactions what we have. So we can write that the oxidizing properties are like this. So we have written that the oxidizing property, if I write some of these properties, we can write that, for example, I can say that SnCl2 when reacts with SO2 and that is in presence of HCl, that is HCl, it will get converted into SnCl4 plus we can get that it is H2O and sulfur. So we'll get that H2O and sulfur, and if you have to balance that, we can write like this. That is twice of this, we'll get 4 times of this, so that I'm going to write that it is twice of this and we'll write that as sulfur. So we get sulfur and H2O, that is twice of H2O. So that is how we can write. And we can write that with Fe, we know that with Fe, if we react with SO2, it is also going to react like this. That is, we are going to get FeS plus FeO, twice of FeO. So I require this. These are the examples, few examples what we have written is. That is the property, that is oxidizing properties for these element tests. Now if we talk about that its uses, then we can say that the uses of this, we can say that it is used as anti-clor. Right? So it is used in manufacture of many substances, in manufacture of H2SO4, sodium bisulfite, ammonium sulfate, etc. we can write that. So it is used in manufacture of these, and that is used in as a bleaching powder. So one is this, another is it is used in reductive bleaching. The reductive bleaching, we used to say that it is used in reductive bleaching, that is temporary bleaching. So temporary bleaching, So that is a temporary bleaching that in presence of sunlight, the color will again reappears. So SO2 when reacts with H2O, it will get converted into SO3 plus, we used to say that hydrogen, the nascent hydrogen is formed. This nascent hydrogen, that is reductive bleaching, will colored matter. So colored matter will get converted into the colorless matter. So we get colorless matter. This colorless matter will again, the color will reappear again in presence of sunlight or on heating. This colorless matter will regain its color, that is color in sunlight or by chemical reaction. So that is why it is called reductive bleaching and temporary bleaching is. So that is all about the sulfur dioxides what we require in this class, and this is all in this classes. So that's all in this class. In the next class we'll continue with that compounds of sulfur. So that's all in this class.